Okay, so now, and I would like to show to you a taste of some experiments that we made more recently on vortices in rotating on stratified flows. So we have waves, but we have also vortices in these flows. And the title is From the Laboratory to the Great Spot of Jupiter. You know that the Great Spot of Jupiter is an enormous anticyclone, and we will see if we can do the same in the lab. Okay, so my colleague, I did that with the students, and my colleague, Michael Lebars from here, from IRFE, Philippe Marcus, and his former student, Pedra Massanzadeh from Berkeley University, and also some of the experiments, if I can go there, were realized in Mexico, in Guadalajara, around Anne Cross and Raúl Cruz Gomez, and their student Hector and Arturo, who were master students at the time on these experiments on vortices. So the question we had was raised by Phil Marcus, who asked us if it was possible to study the great spot of Jupiter in a lab. Okay, so Phil is one of the experts of Jupiter, and in particular, he studied a lot the great red spot. And so these are photos from NASA, and this is a PIV analysis that Phil with the colleagues did on the clouds, okay, of the great red spot. And this vortex so is an anticyclone, so in the atmosphere of Jupiter. And it's quite big, okay? It's an enormous anticyclone. The size is something like 20,000 kilometers, 25,000 kilometers, like that, and maybe 10,000 of kilometers wide here. And you can see, you can put the Earth here in the middle, okay? So it is the size of a complete planet Earth, okay? And because of this measurement by PIV, we could also measure the velocity of the winds inside the great red spot. And you see that you can reach something like 100 meters per second, okay? So it's a very big storm in Jupiter, okay? The estimation of its vertical depth is still an estimation, even if the last probe, Juno, measure maybe something larger than that. But it's a quite flat, okay, compared, so it's 50 or 100 kilometers. This is very small compared to the 25,000 kilometers. Note also that 90% of vortices, the large vortices on Jupiter are anticyclonic, okay. So the first question that we can ask is, what do we need to reproduce in a lab this kind of a vortex? And for sure, we need rotation, okay? So can we generate a vortex using rotation? And that was, this is a video that Oriane, Michael, and John Onu performed in the lab of John in UCLA, and they share this video on the internet. And what you do is you will see, you make you have a pot of water that you put on a turntable, okay, a simple record player. And when you inject dye water, what you obtain, it is what we saw at the beginning of the first lecture. We obtain Taylor columns, okay. So basically, this is what we obtain, okay. So that we can sustain vortices in rotating flows, but they will not be flat vortices, okay? They will be columnar vortices, barotropic vortices. What do we need more? Maybe we need stratification. So let's do the same experiment, but with only stratification. So we have a stratification with salt, okay, as I explained before. And we have salty water here, and you have the stratification to pure water at the top. And we will inject here, or they have injected dye water with a given density, which corresponds something in the middle, okay, to the density in the middle of the continent. So let's do this experiment. And you see, and you can guess what's going to happen is because of the stratification, the water which has a given density will spread, okay, on a layer, on a thin layer like that. And that will be flatter and flatter as far as the layer will extend, okay. So I think you can guess what will be my experiment, the following experiment. So the following experiment will be to have rotation and stratification. And so what is the result of that? So rotation will tend to make columnar vortices, so elongated on the z-axis, and stratification will have a tendency to collapse the vortex on the layer. So these are the two ingredients, in fact, to have this shallow vortices like a great red spot, or like vortices in the ocean, in fact. We have many of these vortices in the ocean. So we will do the experiment maybe more seriously with at least measurement, velocity measurement, and the density measurement. So this is our experimental setup. And this is on the left, this is the stratification here. And you see that we will create a vortex around this depth here, z equals 30 centimeters here. Okay, so and by injection, the same way we did as before. So the two parameters of the experiment is the Grund-Wasserjahr frequency, which is defined as usual, and the angular velocity of the table of the container, which will give the Coriolis parameter, as it is said in geophysics. Okay, so this is again visualization and PIV measurement. So you see that we have this, we inject through, you see we have this pipe, this small pipe here, and we inject water, which is salted at the density at the level here on the middle here. And you see that we can have this kind of vortex. So you see from the top, but you have rotation. And because you inject, in fact, you form an anticyclone, okay? If you have, in a rotating flow, if you have motion that goes radially outward, you will have an anticyclonic motion because of the action of the Coriolis force. And if you pump out water, you will form a cyclone, okay? So in fact, an anticyclone is associated with an increase of pressure and a cyclone with a decrease of pressure. And in a lab, you can make it because you suck water out. So these are the PIV measurements that we did on these vortices. These are the velocity profile. And you will see that we will use the Rossby number to characterize our vortices, which is the ratio between the rotation rate of the vortex, which is given here by that. We suppose that the core of the vortex is simply given by a solid body rotation. And for what I want to show now, this is enough. And so this is a Rossby number defined as the rotation rate of a vortex divided by the Coriolis parameter. Okay, you recognize here the linearized Euler equation, which just said that you have a pressure gradient on the radial direction, which is in geostrophic balance, that is compensated by the Coriolis term. And the Coriolis term, because of solid body rotation, you can write it under the shape. So dp dr is just this term. So rho f omega, the rotation of the vortex, on r, the distance from the center. And on the vertical axis, you just have the hydrostatic balance, okay? And we can write it as we saw before. We can write it as a function of the Grund-Wasserjahr frequency under this shape here, like that. And because we have stratification, you see that the pressure, the gradient of pressure on the side of the vortex here is linear in Z. Okay, so what you do with these equations there, you see that you can, because everything is quite constant, okay, we say that the solid body rotation, so omega will be constant. You can integrate the pressure. So on the radial direction, this will give R squared divided by 2, okay, this here. And on the vertical direction, that will give Z squared divided by 2, okay. So in fact, the pressure has this shape in R and Z in the vertical plane. And if we take isobars, okay, so pressure equal constant, so we say P00 somewhere, you see that these are the shapes of ellipses. And these ellipses have axes, okay, so the horizontal axis is given by this term here, okay, this is a 2L, like that. And vertical axis will be given by 2H, will be given by this term here. And if you make the ratio between H and L, and you call that, so H or D, you call that alpha, okay? And you find that the aspect ratio of the vortex is simply given by the ratio between the Coriolis parameter divided by n squared and the Rossby number. Okay, so more the Rossby number is large, more the H will be large, and this is what we saw in the experiment. Okay, when you increase rotation, you want to elongate the vortices on the vertical direction, and on the opposite, if the stratification is strong, N will be strong, and the vortex will be flat. Okay. Because of viscosity, of course, we cannot sustain these vortices forever. We have some viscous effects, okay? So the vortex will slowly decay. I want to point out that they decay, but not on a simple viscous time, because of this change in stratification between the vortex and the outside water, we have a potential energy there, okay? So we have, in fact, a secondary motion, which is a vertical motion, okay? In the vortices, we have this kind of loops which exist because of the stratification. And because of that, we can sustain our vortices longer than for sample viscous time, okay? Nevertheless, we have less and less energy in our system. And in fact, the Rossby number will decrease. And as a consequence, the vortices will become flatter and flatter. And we can plot that because of the aspect ratio like that, okay? And in fact, we can completely model our vortices by the formula that I explained here, okay? By these ellipses, okay, we can fit our experimental data in black by the ellipses I theoretically determined before, okay? And I can choose the initial Rossby number to have a best fit. So imagine I choose a time and the corresponding Rossby number, and I squeeze my ellipse. Okay, you see that the Rossby number will play with this term here, okay? And so I have the aspect ratio will be the same, okay? But the ellipse will be more or less large. And so you can fit it on the first time, we say t equals t76 here in this number. I think it is seconds. And you can follow in time, okay, exactly the model. You just take the Rossby number, you recalculate the shape of the ellipse, and starting from that, and you can compare it with the experiment. And you see that we have a quite nice prediction of the evolution of the size of the vortex. Because natural vortices have also an inner stratification, we decided also to take into account the stratification inside the vortex. And so that gives a small modification, in fact, a small modification of buoyancy forces. Okay, and you see that in the aspect ratio formula, you have here a difference that appears, which is the n inside the core of the vortice square minus the Brunn's area outside. And because Rossby number can be also large, that is, we can have the centrifugal effect inside the vortex. So we take into account in the pressure gradient the centrifugal term, which is a v square, so along the azimuthal divided by r. And if you take into account this term, you have 1 plus Rossby that appears here instead of Rossby. Okay, and so that was done to be closer to realistic and the real application in geophysics. Okay, so what we compare that, we took first our experiments. So our experiments are the square data here, and we plot this thing, which is the aspect ratio, and we reverse the formula. You see, to have here only the function of a Rossby number. I put here an absolute value of a Rossby because Rossby is negative for anticyclones. Okay, so I didn't want to. I wanted to avoid a sign problem. And so the experiments are here. Okay, so these are the different vortices that we created. Okay, these are the square dots here, but this is in blue. And you remember I started my discussion, my lecture, talking about the vortices on Jupiter. And in fact, there are the two vortices which are well known. It is the great red spot, and we have enormous error bars. Okay, but we are not very far from the prediction from our analysis. And there is also the oval B, which is the name, and it is if you remember some photos of Jupiter, it's a vortex which is not very far from the great red spot, which is it is an ellipse which is completely white. Okay, and if I remember correctly, and we can plot the data we know from astrophysics also on this plot, and presenting these plots to oceanographers. In fact, they pointed to us that there are some internal vortices in the oceans. We know that we have also surface vortices on the ocean that we can study by satellites, but we have also these vortices inside the water. I would say something like 1,000 kilometer depth. And these vortices, for instance, and I know that because it's close from Europe, are generated at the Gibraltar Strait. Okay, in some circumstances, when I think it is when the tides are high, or for I think it is in autumn and spring, the currents are quite high. Okay, quite strong, and the Mediterranean Sea, plunges under the oceanic water. So the Mediterranean waters are warmer because they are warmer, so they should be lighter, but they have a lot of salt. Okay, and in fact they are denser than the Atlantic Ocean water, and so they dive under it, and they can generate internal vortices that are called MEDIs. And these MEDIs are about 100 kilometers wide and something like 1 kilometer or several hundred of meters thick. Okay, so they are big animals. Okay, and they are emitted from the water from the Mediterranean Sea, and they can travel in the North Atlantic something like several years. Okay, and so they can transport Mediterranean Sea very far away from the Gibraltar Strait. Okay, and very farther than if it was a simple jet. Okay, here the vortices go very far away, and we think they can cross the ocean and go up to the Gulf Stream there. Okay. So if we the oceanographers study these medleys, and they know quite well the shapes of the medleys. And we plotted the shapes and the density and the Rossby number and the medleys. And we plotted here but some data that we knew from these medleys, and you see that they respect quite well the law that we calculated. Okay, and I think it's time for me maybe to stop now. I want to go for question if you have some question.
Okay, thank you very much, Patrice. To start with, there was a question from Adèle Moncuquet, who I asked to keep for the end because it was a kind of a general question. So it's in the chat.
Yeah, so there is a question with that said, so how does the great red spot vertical length has been determined? Okay, I'm not a specialist of the probe of the NASA people, but I know that they can measure the constitution of the atmosphere. Okay, they can do that by the size or by spectroscopy, and they can guess also what is the constitution of the great red spot. And if I remember correctly, Juno can measure maybe by radar, or maybe Juno could measure the pressure also. Yes, maybe they send a probe to measure the pressure. I'm not sure of that, but this can be checked on the NASA website very easily. Okay. So this is sorry, I'm not a specialist of the great red spot myself and of Jupiter myself.
Thank you. More questions? People can also ask the questions directly if the mics can be if they can activate their mic.
Yes, what I said yesterday is I will send a PDF of my slides, and that will be posted, I think, on the website of the school. And if people want to ask questions, okay, they can send them by mail. Okay, I will be happy to answer these questions.
While we are waiting for questions, I had a few questions. First, to make sure I understood well the design of the experiments with the sphere. So all the space between the sphere boundary and the cylinder is filled with silicone, right?
Yeah, that's completely correct. Yeah.
And then just inside the sphere it's empty, so you can put water.
Yes, there. we have a little tube, and we can put water. So with a cylinder.
So when you have your rolls that apply pressure on the cylinder, they actually deform the sphere. That's the idea. We
deform a sphere in a yes, absolutely correct. Yeah. So that was that was the first version of the experiment, with a sphere was several centimeters wide, and after we asked a company to cast a sphere in silicon, the same principle, but it was maybe 15 centimeters wide. So it was wider, and the Reynolds number was wider, and we can go to more to turbulence ranges and so on. Yeah.
Okay.
And maybe to complete this answer, and on the after, Michael Lebas realized that these instabilities coming from resonances can also be triggered by over motions of planets on course, like precession. Okay, so if you have a precession, you also trigger, and you also complete the resonance, but with a m equal 1, if I'm correct. Okay, or precession or mutation or libration also, and so there you do not need to have soft container. So the experiments are simpler to perform, because you have elliptic containers or spherical containers or cylindrical containers, which are solid, but you can precess or have mutation or any kind of motion you want to do, and you can make these waves to resonate, this inertial wave to resonate inside the containers, and to have instabilities. And this is, of course, relevant also for planetary cores or for stars because these rotation are not pure rotation. Okay, sometimes we know that the Earth has a precession. Okay. And if I remember correctly, we are also slightly under the threshold to imagine to have a dynamo due to precession.
There's another question from Adele on the chat, right on the slide that we are having, that we see. She's,
so, yeah. Yeah, I read the question. So the question is the linear trend. Can we observe a linear trend for a small value of alpha and Rossby number? So experimentally, it's quite difficult to have a small, very small Rossby number because the vortices are not very strong, the velocity are very small. So that I cannot say. Maybe we can check something, which is I can go further in my lecture, but in fact, I skip if I can. Oh. So what I wanted to do is I wanted to, yeah, so we study also surface vortices, okay, but and we, so you see it's a vortex which is made as before, but without any stratification. It is just pure water in green above salt water, which has a given density. Okay, and we made the same kind of study, and so I don't want to go through the slides, but yes, where oh, sorry, I do not have a slide I wanted to show to you. Let me go. Where is it? It is there. Yes. Okay. This is a slide I decided not to present, and finally. Okay. So you see, so these are our experimental data here. Okay. And so the units are not exactly the same as before. Okay, we just plot here the epsilon square. Epsilon is a small parameter, whereas take into account the fact that the vortices are not solid body rotations, but they are Gaussian vortices. When you have Gaussian vortices, you can still integrate the equation of motion, but you have a new parameter that I call epsilon, which is not that important. Okay, and so this is the prediction of the aspect ratio. Okay, so these are our experiments in the lab on these surface vortices, floating vortices, and you see we go to very low value here of Rossby and f squared divided by n squared, and these are data from floating anticyclonic lenses in the ocean. Okay, and you see that for some of them it's quite good, but several of them, maybe 2/3 of them, do not respect. In fact, 2/3 of them do not respect this law, even if you can see that there is a general trend. Okay, so the scaling here, this is f square n square Rossby, is certainly respected in a certain way, but certainly what I think is, so that this is my answer to the question you asked. Okay, we can try to do the same thing for on the left side of the experiment, but certainly that the exact shape of a velocity field. So in the lab, I have this epsilon for Gaussian vortices. We have certainly to take that into account to have the exact aspect ratio. So what is the exact shape of a velocity field to have corrections? Okay. So certainly I can guess that these vortices have very sharp wall on the side. Okay, they are very, very sharp like that. Okay, I can guess because of the aspect ratio is higher than what is predicted. Okay, I hope that was the answer to the question.
More questions? Yes, Anubhab had a question on the chat.
Yeah, I will look to that. Stratified vertical plane quad flow is linearly stable. Yes. You have shown that stratified. Yes. No. Here I don't understand the question. Stratified. So the question maybe stratified vertical quad flow is linearly stable. No, it is. I think it is unstratified vertical plane quad flow is linearly stable. And I showed that the stratified horizontal plane quad flow is unstable. Is it what you mean?
So I was asking that when you have the stratification and the flow in the same plane, you have looked at horizontal plane quad flow, right? So I was thinking that the problem where the flow gradient, the gradient direction is also the gravity direction. So the stratification is in the plane.
Yeah, so this is the situation that was considered by Paul yesterday lecture, yes?
Right, yeah.
Yeah. No, so I didn't. I didn't look the situation. I didn't look the situation because of what explained Paul, okay? So this situation has been explored a lot in the past. We know that we have Richardson number critical, where above which there is an instability. You are correct to say that. You are correct to say that it is linearly unstable above a given Richardson number. And so this is the Miles and Howard theory. Yes. But myself, I didn't look at that.
Okay. Thank you.
Okay. I wanted explicitly to avoid this instability. Okay. So that's why we put stratification in the over shear perpendicular to stratification. Is it a good answer to your question?
Yeah, thank you.
Thank you.
I had one more question just for the sake of understanding what you said. So when you explained your the instability for the sphere inside the cylinder, so in real life, the role of the deformation cylinders could be played by the gravitational dipolar attraction of moon and sun, right?
Correct.
That would create the same kind of
yes. The same way we know that we have a deformation of the surface of oceanic water, okay, and we have 2 tides per day to simplify it and to neglect the continents, okay. We know that it gives an elliptic shape like that, okay, and so this is the reason why this instability was thought that it could create a dynamo inside the planetary cores. That was a big idea of William Malthus.
Are there any observations on the Earth or stars or planets that show the presence of this instability?
Yeah, that's not obvious because you have to know what is inside the cores. But what we did is that we worked with an astronomer who gave us the data from exoplanets. And we know that the exoplanets, which are called the hot Jupiters, are Jupiters. They are bigger even than our Jupiter. And they are called hot because they are very close to their stars. And there they know that there are very big deformations of the radius. And so as I said before, it's very difficult to estimate the viscous terms, okay? So we know for sure that in these conditions, because of the rotation rate and so on, some of these exoplanets should should sustain this instability, the elliptic instability. Okay, we don't know really where is the threshold, but it should. And we had a hope that it, or how to say that, we have a hope that in the interpretation of a dissipation, we can have an extra term, okay, because of a dissipation by this instability. So, and this will hit the planet a little bit more because of this extra dissipation. And this might explain why some of these planets, you know, when they make a model of these planets or model of the stars, they are a little bit larger in radius, but what they think what they should be. And this is called a radius anomaly. And what we saw in one of our papers with this astronomer is that this radius anomaly of this exoplanet exists for stars or planets, exists when the elliptic instability was present. And there is a correlation between these two. There is a correlation, clear correlation. Now, you know what, this is not a causality, okay? We are not sure that this is the only origin, okay? You have also the tilted axis of these exoplanets. But exactly the same way you saw in the experiment that the flow is tilted in the sphere. There is when you have two stars or an exoplanet close to the star, we know that there is an axis of rotation of both are tilted. So we claim also that it might be the same effect of this mode, okay, the tilt over mode, okay. This is, by the way, the same instability that I presented yesterday with my little spherical solid object that I rotate on the table, okay. You remember where it goes from pink to yellow and so on. And so this is exactly the same instability when you consider solid body rotation. Okay, you tilt the axis of rotation.
Thank you. I don't see any more questions on the chat. I'll give anyone last chance to ask a question. Otherwise, we will stop here.
Okay, so thank you everybody and to the organizers to give me the opportunity to give these lectures, and it was a pleasure.
Yes, it was a pleasure for all of us, I'm sure. So we will reconvene in 18 minutes. So at 3:45 p.m. Indian time, or